Okay, so for instance, if you want to maintain a certain flow rate in your blood vessel, if we'll come to this later, but if you want to make flow rate being, let's say you want to pump 1 gallon a minute of blood. If it's turbulent, then you have to maintain a much higher pressure. Your heart would have to work harder. Okay? So turbulence is a fluid in motion transitions from steady laminar flow to turbulent flow above a critical speed characterized by the Reynolds number. Okay, so above critical speed that happens. Okay, so here's laminar flow. See, these guys are moving parallel to each other. This is turbulent flow. So turbulence is characterized by chaotic changes in pressure and fluid velocity. So you can stand here and measure the fluid velocity and it'll remain steady. You try and measure the fluid velocity here, it's changing chaotically. Okay, and you guys have seen turbulent flow when you see eddies in waters and stuff like that. You know? Okay, so here's blood flowing in blood vessels. This is laminar flow, and here's plaque deposit. And when you have plaque deposit, blood will flow faster here, and then you have turbulence there. Okay, what this graph tells you is this is flow rate. That's how many gallons are flowing a minute, and so to make a fluid flow, if there's friction, you have to maintain a pressure difference. The pressure here has to be higher than this pressure. And that pressure difference is this perfusion pressure. Okay, so look, once the fluid becomes turbulent, you have to have this much pressure difference to maintain this flow. If it was laminar flow, all you needed was this pressure difference. So you're having to work this much harder for the same pressure difference. Okay? It turns out that the pressure difference, when it's turbulent flow, the pressure difference goes as speed square. So for the same speed, if you double the speed, you only have to double the pressure here. If you double the speed, you have to quadruple the pressure. Okay? So for instance, if you go for a run and you want to increase blood flow, your heart would have to work much harder. Okay, so turbulence is bad, okay, in most situations. Viscosity is friction in a liquid. Okay, it characterizes the degrees of internal friction in a liquid. It causes resistance when two adjacent layers of the fluid move relative to each other. So when this fluid is moving, and if this was moving faster, there would be friction between this and this layer. Okay. What does friction do? Friction, it converts kinetic energy to heat. Okay. So it converts good energy to bad energy. Okay. So friction causes part of the kinetic energy of a fluid to be converted to internal friction. So where did that kinetic energy go? It got turned into heat. Okay. So I mean, what we would like is, let's say we are pumping oil from Alaska. What you'd ideally like is you push the liquid once and you want it to come to Florida. Of course, it doesn't do that. What happens? You push it and it stops because of friction, and then you have to keep pushing it again. Okay, so you have to spend energy doing that. We won't consider friction right now. Okay, we'll consider an ideal fluid. So we can apply our stuff to water, gases, and stuff like that. We can't apply it to honey. Okay? We'll mostly apply what we say to gases where friction is negligible. Okay. So we'll consider an ideal fluid flow. It will be laminar. Fluid is non-viscous. The flow is steady. Okay, so the speed is not time dependent. It is incompressible. compressible. Gases are compressible, but we're not compressing them enough where what we're saying will be untrue. So we'll consider incompressible gases. And irrotational. Irrotational meaning this is just eliminating turbulence. If you put a paddle, you don't want the paddle spinning. A paddle will spin when there is turbulent flow. Okay? So that's what we're saying there. Okay? All right. So the first law we want to consider is the equation of continuity. Okay, all that says is here's a tube whose cross-section is changing. Well, I don't care if the cross-section changes. Let's say if 1 gallon a minute flow in, how many gallons a minute are flowing out?
1 gallon.
1 gallon. Okay, if there's no leaks, the flow rate should be the same at every point in the pipe. And here's the flow rate. This is the flow rate. Area of cross-section of the pipe times the velocity of the fluid at that point. So you can see that if the area of cross-section increases, the speed decreases. Okay. And so thicker the pipe, slower it's moving. Okay. Well, you know this because you use a garden hose. You're watering a plant, and when you want to water something that's further out, what do? You narrow the pipe. You narrow the pipe, and the speed increases, and that water goes further. Okay. And that's what those guys, the firemen, also have to do. Water is coming in fast, and when you want to squirt water at a higher floor, you narrow the pipe so it goes faster. Okay? But now you also understand why they have to work out so much, because let's say you're shooting something, you get a recoil, so you got to hold on to the pipe without flying and stuff. Okay? Anyway, here's the equation of continuity. You increase the area of cross-section, the velocity decreases. Okay. Let me show this to you. Okay. Okay, so here's the speed. So you see, I increased the area of cross-section and the speed decreased. Now let me show you another thing. Okay. So here's pressure. So now this simulation is for a non-viscous fluid. Okay. So this is a frictionless fluid, so you didn't have to maintain pressure difference to make the fluid flow. For real fluids, the pressure here would have to be higher than the pressure there. Okay, but right now we'll go with that. Okay, so the pressure here is 120 kilopascals. Okay, now let me do the following. Okay, I'm not going to change the area of cross-section of the pipe, so the speed of the fluid has to remain the same. Okay. When this thing rises, what happens to the speed? I'm sorry? Okay, as this thing rises, what happens to the speed? It decreases. Okay. All right. The speed didn't change. So how did the liquid do that? All right, so here's what had to happen. Everybody understand that? So There was a pressure there. The pressure had to decrease. Okay. All right. So now you had to push it to maintain that speed. Okay. So the relationship between speed, elevation, and pressure was discovered by Mr. Bernoulli. Okay. And go ahead.
So do fluids flow easier uphill? Upwards?
No. So, okay, assuming this is no friction, there's no friction. You had to maintain that speed because the flow rate couldn't decrease. So the pressure here had to decrease. Okay. So if the pressure here decreases, now you're adding force, you're doing work on it to lift it up. Okay. So it's like going back to this analogy. Okay, well, the speed was decreasing, so to maintain that speed, I had to maintain a push. Yeah. All right, so pressure in a fluid varies as it moves through a region where it speeds up and or elevation changes. So the pressure decreases when the fluid rises up. Okay, so the relationship between fluid pressure, speed, pressure, and elevation was derived by Mr. Bernoulli, and here's what he discovered: the pressure at any given location times this is the density of the fluid and the speed square. So this is the kinetic energy of the fluid per unit volume. And this is the potential energy of the fluid per unit volume. Okay. And the sum of these three terms is constant. So anywhere in the fluid, you take the sum of these three terms, and that's constant everywhere. Okay. And this is a very important relationship, Bernoulli's equation. And here's what I want you to remember. Okay. In most situations that we apply, okay, P1 plus 1/2 rho V1 squared plus okay. In most situations we apply, this term will be equal to that term. Okay. So we'll erase that. Okay. Now here's what I want you to remember. So you see P1 plus 1/2 rho V1 square equal to P2 plus 1/2 rho V2 square. If a liquid speeds up, if a fluid speeds up, then the pressure there decreases, because the sum of these two has to equal that. So if this term increases, this decreases. Okay. Whenever a fluid flows faster, the pressure there decreases. Okay. So let me show that to you. Okay, so the pressure here is constant. How can I make the fluid flow faster there?
Lower the back on
Yeah. I narrow it, the fluid flows faster and the pressure decreases. Okay. So anytime, so if you want to decrease the pressure in a fluid someplace, what do? You make the fluid flow faster. Why would you want to do that? Let me show you a situation. Okay, let's say you want to decrease the pressure at the top, then at the bottom. Why would you want to do that? If you wanted to lift some object, okay, you want to decrease the pressure here. You got to make the fluid flow faster there. How do you make the fluid flow faster? You design the surface like that. This air has to travel a greater distance, so it'll have to move faster. There's your design of the airfoil. Okay. So pressure at the top, pressure at the bottom. Okay. So fluid is flowing faster at the top, so pressure at the bottom minus pressure at the top times the area is the upward force, which is equal to lift. Okay. So that understanding of your equation allowed you to keep a metal object up in the air. Okay. So here's another effect. You might have seen this. So when you pass a semi or something like that. So now before you guys were driving there, air was flowing like that. And now these two vehicles come and all this air has to move through this narrow gap. So this air is moving faster than this air. The pressure here is less, so you feel an attractive force towards the semi. Yeah. So this airfoil is designed to make airflow faster here than here. Okay, and since air flows faster here, the pressure at the top is lower than the pressure at the bottom, and that provides the lift. So the pressure difference provides the lift. Okay. So here's a computer simulation of that. So here's this, the plane is flying this way, so the air is moving relative in the relative to the plane, the air is moving in that direction. And you see this top air traveled faster than the bottom air. The pressure difference because of the speed difference accounts for most of the lift. Okay. So pressure okay. The faster the speed, lower the pressure. So when this laminar flow is broken, when turbulence happens, so this is when a plane stalls, okay, if the angle of attack is too large, now you suddenly lose lift and drag increases as well. Okay, so because pressure is chaotic here when laminar flow breaks, so you're losing lift and drag is increasing as well. Okay, and you can fall off from the sky. If you play tennis, you use top spin, and the reason you do top spin is the following. Okay, so if you hit a flat ball, the ball will go outside the court. But now if you hit with a top spin, what happens is the ball, there's a force on the ball, and it'll always make it fall inside the baseline. The greater the top spin, the greater the downward force making it fall inside. Okay, so the harder you hit, the more likely the ball will be right. Okay, so when you hit the top spin, the ball is going this way, air is flowing this way, and the felt on the ball makes the air flow go like that. This air has to travel faster. The pressure here is lower, the pressure here is higher, and that is providing that force, putting the ball down.
The speed of the bottom of the ball is faster.
I'm sorry?
The speed at the bottom of the ball is faster.
The speed of the air flowing, yeah. So all these things in aerodynamics, what you're doing is you're controlling the airflow. You're changing the airflow to your advantage. Okay? And so control surfaces on an airplane, that's what they do. They're changing airflow, so the forces that come into play do what it is that you want to be done. So here's this is called the Magnus effect, and you guys might have seen this. Okay. Have you guys seen this guy?
Recently, some friends of mine went to the Gordon Dam in Tasmania, which is 126.5 meters or 415 feet high. Then they dropped a basketball over the edge. You can see that the basketball gets pushed around a bit by the breeze, but it lands basically right below where it was dropped. Now watch what happens when they drop another basketball, this time with a bit of backspin. Whoa, look at that go!
This is Brett who just threw it. I literally just dropped it with a bit of spin, like I didn't even throw it, and it just took off. Like we had no idea that was going to do that.
And this is where I come in. The basketball was subject to...
Okay, so you spun it like that. There was air flowing around like this. That air was flowing faster. The pressure in the front was smaller, and it went forward. So these atomizers that you use, the squirt spray bottles that you use, what is happening is you're just blowing air across here. Air moving faster, the pressure decreases here. So this becomes less than 1 atmosphere. This is 1 atmosphere, and that higher pressure pushes the fluid up. And that fluid gets caught here, and so this air and this fluid is squirted out there. Okay. That's how you drink in a straw too. When you drink using a straw, it's the atmospheric pressure pushing this liquid up. How do you decrease the pressure here? Huh?
Reduce the area.
I'm sorry?
Reduce the area or increase the speed.
Okay. Here is the ideal gas law. Okay. If you increase the volume of air, the pressure decreases. So when you're sucking, you're lowering your diaphragm, you're increasing the volume of your lung. So the pressure of air in your lung decreases. Mm-hmm.
So when we drink through a straw, it's working with the same process.
Mm-hmm.
Does that mean that there's like a limit to how far up a straw you could?
So, okay, good. So very good question. So the atmospheric pressure can support a column of air that is 10 meters high. So the best you could do is create vacuum if you were Superman. And so 10-meter long straw is the longest you can drink water with. If you want to drink mercury, what is the longest straw you can drink with?
14 times fluid.
No, yeah, so 76 centimeters.
Oh.
Yeah, okay. And there you go. You could drink alcohol with a longer straw. Alcohol is less dense. All right. So viscosity, what is viscosity? That's friction in a liquid. Okay. Here's viscosity.
Recently, some friends of mine went to the
eta,
Gordon Dam in Tasmania, which is
and, here's how you
126 and a
measure it.
half meters,
So you
or
would use,
415
let's say,
feet
wooden-
high. Then they dropped a
wooden
basketball
boards,
over the edge.
Put the liquid there.
You can
and what
see
you
that
do
the
is
basketball
you
gets pushed
pull
around
on
a bit by the
stop
breeze,
board.
but it
You
lands
measure
basically
the
right
force
below
that's
where it
needed
was
to
dropped.
maintain a constant
Now watch what
velocity.
happens when they
All
drop
right, ready?
another basketball, but
If
this
there was
time
no
with a bit
friction,
of
if you had
backspin.
applied a force, then this top
Whoa,
board
look
would
at that
accelerate.
go!
Because of friction, you have to apply this force to maintain a constant velocity.
So you want
And
those
so
to get back
the
in the water,
viscosity
do
is the force you apply,
This is Brett who just threw it.
and the velocity.
I
of the board
literally just
divided
dropped
by the
it
area
with a bit of
cross-section
spin, like I
times the
didn't
area
even
of
throw it,
cross-section
and it just took off. Like we had no
times
idea that was
divided
going
by
to do
the
that.
distance between these.
And this is where I come in.
That's how you would
The
measure
basketball was
viscosity.
subject to
And if you have viscosity, then you have to maintain a pressure difference to make a fluid flow. If their viscosity was 0, you didn't need any pressure difference to maintain a fluid flow. You saw that in the simulation. Okay. So this is flow rate. There's the pressure difference. The pressure difference you're maintaining, how are you maintaining the pressure difference? Your heart is beating, is doing the work to maintain the pressure difference. Here's pi, radius of the blood vessel, to the power 4. 8 eta, the viscosity, divided by L. So here's a couple of applications. Okay, when you're pumping oil in Alaska during the winter, oil is cold, and when it's cold, the viscosity increases. When the viscosity increases, to maintain the same flow rate, you have to increase the pressure difference. Your pumps have to work harder. You're spending more money.
So you want to pump oil where it's hot?
Hmm?
You want to pump oil where it's hot?
Okay, yep. Or what else can you do?
You know,
There you go. So there are heaters around the pipe. When would you do that? If the money you spend on heating,
it's less.
yeah, there you go. So it's all cost benefit analysis. So that's why you heat the pipes up. Okay. Now here's another very important thing. Okay. There are times when you want to increase the blood flow by, let's say, a factor of 4 or 5 in humans. When you're doing vigorous exercise, or when you have a big meal and then blood has to go into your intestines and stuff like that. You have to increase the flow by a factor of 5, let's say. And this is real. You don't want to increase the pressure by a factor of 5. Your heart, you don't want to make your heart work that much harder. Okay, look at this. All you have to do is, let me tell you. Okay. So if you increase the radius by a factor of 50%, your blood flow would increase by a factor of 500%. So that's what athletic training does. Well-trained athletes, if I go for a run, my body is not conditioned. My body doesn't know how to increase the blood radius by, my body just does the stupid thing. It just increases pressure. Okay. So, but if I train like her, my body will learn to increase the radius. All right.